Hello, Longhorns. Today we're going to take a look at lesson number 20 on the laws of thermodynamics. This will be a very basic intro of what can really turn into a really deep concept. But if you remember from our last lecture that heat is represented by the letter Q, and heat can be transferred through conduction, convection, and radiation, you should be pretty good. We're coming from pages 340 through 355. Now, there are two laws in particular that we're going to keep up with. The first law of thermodynamics is something that actually is really familiar. It should remind you of the conservation of matter, the conservation of energy. And it tells us that heat energy cannot be created nor destroyed. No matter what process we're doing, and no matter how efficient we really wish to be, we know that somewhere in our system, somewhere in our processes, we will lose energy, or energy will be transferred into another form that's not usable for exactly what we're doing. Now, Q, capital Q, represents heat, and capital U is going to represent the internal energy, the amount of energy that is found in a system. We're going to find that when we add these together, the goal is for us to come out with equal amounts. So whatever we started with, we should end with. But for some reason, trying to get to 100% efficiency isn't possible. By the end of this lecture, hopefully you guys will be able to tell me exactly why. Now, when isolating your first law of thermodynamics, we have to remember that there's a clear relationship between our variables. Remember that U was your internal energy, so it's in there. Q is heat, and capital W stands for work. So if I think about a change in my internal energy, I can do heat minus work and come up with an equation that should satisfy this law. Now, it's vital to keep up with whether my Q or W are positive or negative. This tells me if the system gained heat, lost heat, or whether work was done by the system or on the system. As we go through examples in class, we have to be very specific as to what our positive and negatives mean. Usually we're able to use those just for directional terms, but moving forward for your first law of thermodynamics, it simply tells you what is working and what's not working, and what's simply a part of your system. Now, if you think about it, your internal energy of a system is going to depend on its temperature. In this example, we have a young lady that's going for a run. So I want you to compare yourself to just before you start to run, and then 30 minutes into the run. Most of us, by that point, are breathing a little bit harder, and we're also sweating. So we know that heat is being given off. In your mind, you're thinking, if heat's being given off, some work has to be done. So there's a change in your internal energy. You're coming back to the equation for the first law of thermodynamics. You've never had to think about it before. But if we look here, this is your heat. We know it's going to be some changes there. My U decreases, and U is your internal energy. It's going to decrease. And then the amount of work being done will increase because we've actually got to move this complete system. When looking at motion, and you're probably thinking, what could we use this for? When we have to add parts to the body to restore function, one of the things we take into consideration is how long will this body part that we've created, how long will it be able to function? What will it be asked to do? So what are the requirements on it? And then what are those things that could keep it from being as efficient as possible? Just with any machine, any engine, car, jet, or boat, anything else you can think of, we want to put those same questions in the front and forward so that we're able to create things that are important and helpful. Now, here's an example. Heat is added to a system, and the system does 26 joules of work. So if the internal energy increases by 7 joules, how much heat was added to the system? Now, we've always used our guess method to tackle our problems, and this is a good example of how that can be helpful for us as well. So let's take a bigger look. Heat is added to a system, and the system does 26 joules of work. So for my given, my W is 26 joules. If the internal energy increases by 7 joules, so my change in U is 7 joules. How much heat was added to the system? Your unknown is heat, and we use capital Q to represent that. Your new equation is a change in your internal energy will equal Q minus U. All right? Now, before we go forward, let me go back. Let's double check this because I can't remember if it's a minus or a plus. So really quickly, I think we have those lined up. And this should be, instead of U, I should have a W. So whenever something doesn't feel right, take the time to go back and double check yourself before you continue forward. So, substitutions, nothing needs to be made. We have energy, which is given to us in joules, which is our correct unit for energy. So let's combine our substitution step. And we need to solve this equation for Q. Whatever happens here, guess what? We're going to do the opposite. So this is what I start with, Q minus W. I am going to add W to both sides. So I end up with delta U plus W equals Q. U is going to be 7. The amount of work is 26. And then I have heat. 26 plus 7 should give me 33 joules. And that will be the amount of heat that was added to your system. A lot of these problems are very straightforward as long as you're able to identify your variables. Now, energy deals with joules, work is in joules, and we have also been able to locate heat. Because that heat was positive, we know that there was something going on in the processes or in that particular system. Second law of thermodynamics is very straightforward. When objects of different temperatures are brought into thermal contact, heat is going to flow in one direction. It likes to go from where it's warmer to where it's cooler, and it does not go backwards. There are 2 videos that are attached to this particular PowerPoint that are very good examples and even take a nice camera view and show you your thermal energies in different colors. It uses a cup of coffee as one example and then an ice cube that's melting in a glass as another one. I highly recommend you take a look at these 2 videos to kind of get an idea of where we're going when we're talking about heat and, of course, thermodynamics overall. Now, if we're trying to be as efficient as possible, if I ask you what's the best percentage to have, you guys will tell me 100%. In the real world, do I actually start and end with the same amount? Am I going to have 100% transfer from the beginning to the end? The answer is no, not possible. Somewhere along the way, we're going to lose a little bit of energy as either heat or it can transfer to other things. So 100% efficiency is not an achievable requirement, but it is a gold standard. Your textbook gives you the equation of efficiency is equal to the net work done divided by the amount of heat. It puts it in QH. Another way to look at it, because sometimes we do use percentages, use for energy output divided by the energy input multiplied by 100%. All right? Now, let's see if we're able to calculate how efficient something is. This is important when you're looking at different engines or different compartments. When you're looking at things like your washer and dryer, your dishwasher, or even your refrigerator, the things that can keep your electricity bill low. We have a test model of an experimental gasoline engine does 45 joules of work in one cycle and gives up 31 joules as heat. What is the engine's efficiency? I don't know, those numbers are kind of big. So let's set this one up and see what we get. We have, for our given, we were given work of 45 joules. They also told you that you're giving up as heat for Q, 31 joules. And we've been asked to calculate efficiency. Now, the equation was straightforward. Efficiency is equal to the net work that's done divided by Q. All right? Both of my units are already in joules, so we're looking good. No substitution is needed. So efficiency will be equal to 45 divided by 31. Let me grab a calculator. If we take a look, 45 divided by 31 will give me 1.45. I can leave it here, or I can take it one step further, and we're looking at 1.45. Now, if I want to compare the engines to something that's already in production, what I know I want to do is take this number and calculate it out for each engine type. We're looking at how much change is going to take place. If this is my amount of work and the amount of heat that's being lost, there's no way, even in the conservation from the first law of thermodynamics, that I'm thinking I'm going to recapture 100% of what I started with. So here's your basic walkthrough and answer. Before you go, these are the two videos that have been attached to do a really good job of showing you just how we're using the first and second law of thermodynamics. If you have any questions, feel free to send me an email, and I'll see you guys in class.